I'm Luheng. So my talk today is mostly focusing on our most recent work on neuro-semantic role labeling, what works and what's next. And another tentative title would be, what else can we do other than using 1,000 LSTM layers? This is joint work with Kenton, Mike, and Luke. So I will start with a brief overview of the semantic role labeling task. What are the interesting and challenging aspects of it? So the motivation of doing SRL is that we want to find information such as who did what to whom, when, and where from the text. And if we view it as a structure prediction problem, the goal is that given the predicate, we want to identify all the arguments in the sentence and assign semantic role labels to each of the arguments based on their relations. SRL can be used as an intermediate representation that can benefit many downstream applications, such as question answering, information extraction, or machine translation. So to understand the problem better, let's look at first two example sentences. The first one says, the robot broke my favorite mug with a wrench. And the second one says, my mug broke into pieces immediately. And the syntactic structures of the two sentences look roughly like this. My favorite mug in the first sentence is the syntactic object of the verb broke, and my mug in the second sentence is the syntactic subject instead. However, even without going into details of the SRL formalism, you'll probably agree with me that the mug in both sentences correspond to the thing broken in the breaking event. And following the same intuition, we can say the robot is the breaker, the wrench is the instrument used for breaking, into pieces is the final state, and immediately describes the temporal attribute. Now, if we're given a lookup table about the semantic role labels, which is called a frame file, we can assign the semantic role labels to each of those arguments based on the descriptions. So we can say the robot is the argument 0, my favorite mug is arg1, the wrench is arg2, so on and so forth. And this is basically what the semantic role labeling task does. We can model SRL as a supervised learning problem thanks to the release of the proposition bank, which is the prop bank. It's annotated on top of the pantry bank syntax, which means that the semantic arguments in prop bank are mostly the syntactic constituents in pantry bank. It has a set of core rows, which are the verb-specific rows numbered from arg0 to arg5. And the actual meanings of those rows are defined in the frame files. For example, the argument 2 of break is the instrument, but it can be something completely different. For example, it can be the seller in the verb buy. It also has a set of adjunct rows, which with the prefix argm, and they're shared across all the different verbs. And those are used to describe the modifier attributes of the semantic structure. So they can have temporal, location, manner, direction, cause on purpose, etc. So even in the supervised setting, semantic role labeling is a quite challenging problem. For the first 10 years since prop bank has released, the model's F1 on the prop bank's test set has improved modestly. It went from 79.4 to 80.3. So to understand the difficulty of the problem requires understanding the unique challenges of the SRL problem, such as syntactic alternation, propositional phrase attachment, long-range dependencies, and common sense reasoning. So in the next few slides, I'll go through each of these challenges with some examples. So here are 3 sentences, all about some playing of music. First says, the robot plays piano, the cafe is playing my favorite song, and the music plays softly. And the syntactic subjects of the sentences are the robot, the cafe, and the music. But they can correspond to different semantic roles, such as arg0, the player or the performer, or arg1, the thing being performed. And the objects of the two sentences are piano or my favorite song. They can be either arg2, instrument, or arg1, the thing being performed. So this means that there's no fixed mapping from a syntactic structure to semantic structure. And in order to predict the semantic flows accurately, the model needs to consider the lexical context or the sense of the verb, etc. So this brings up another problem, which is the prepositional phrase attachment issue. So if I say, I eat pasta with delight, the prepositional phrase with delight modifies the verb eat, and it describes a kind of manner of eating. And for another sentence, I eat pasta with broccoli, the prepositional phrase with broccoli modifies the noun pasta instead. And the whole phrase pasta with broccoli is the entire argument one. So to get this right, the model needs to know that delight means some sort of emotion, and broccoli is a kind of food that can be eaten. And for a lot of the cases, the semantic flows and the argument of a predicate is very close to the predicate in the surface string, and is the direct syntactic child. So, for example, in we flew to Chicago, it's sort of an easy case for the model. But if we say, we remember the nice view of flying to Chicago, the argument we is no longer the direct syntactic child of flying, and it's also very far away from the predicate in the surface string. And if we change the words a little bit, say, we remember John and Mary flying to Chicago, there is some ambiguity here, but probably John and Mary are the passengers flying to Chicago. So also the model needs to know that John and Mary, or we, are people who can fly in a plane, and the Niceville is something that doesn't fly. So if we go to the land of out-of-domain data, SRL can be even harder. Say, for example, if we want to build a cooking robot that tries to understand recipes and read something like dip chicken breast into eggs to code, it will probably misunderstand to code as the actual noun to code, because it has never seen something like this in the training data. And similarly, if we want to build SRL system for biomedical text, we can probably imagine the model complete fails. I can't even read the sentence here, but. So our long-term goal is to improve semantic flow labeling and make it useful for many different domains. And the first step is to collect more data cheaply, so that we can collect data for many different domains. In the next few slides, I will describe the work we've done for collecting data. And the next step is to build an accurate SRL model starting from the prop bank SRL, which will be the focus of this talk. And the third step is to combine what we have done for the data and for the model, and try to build a very useful SRL system. So for data collection, our intuition is that anyone who understands the meaning of a sentence should be able to provide some sort of annotation for SRL. But it's very challenging if we want to do this for the prop bank, because, for example, the prop bank has an annotation guideline of 89 pages, and it's very, very hard to train non-expert annotators to do this reliably. So our solution is that we designed a much simpler annotation scheme, which is very simple and intuitive, so that non-experts can do it. And this is what we have come up with. It's called question-answer driven semantic flow labeling, or QASRL. So here's the task. Given a sentence and a verb, last month we saw Grand Canyon flying to Chicago, and the verb flying. The first step is to ask a question about the verb, for example, who was flying. And the next step is to answer the question using words in the sentence. So here the answer is single word we. And we can repeat the process and try to write as many question-answer pairs as possible. So we can ask, where did someone fly to? Answer Chicago. And ask, when did someone fly? And answer last month. And we do this over and over and stop until no more question pairs can be written. So basically, this is our entire annotation task. I've just showed you in one single slide, and hopefully I've convinced you that it's indeed simple enough. So compared to prop bank, the question-answer structure corresponds nicely to the predicate-argument structure, because the answers correspond to the arguments in prop bank SRL, and the questions can be used to describe the semantic flows. because we are using natural language questions, we no longer need to predefine a set of roles. This also greatly simplifies the annotation process. So if we show the QA-SRL structure with the prop bank SRL side by side, you can see the questions correspond nicely to different semantic roles. And in fact, our non-expert annotated QA-SRL has about 80% agreement with the prop bank. So we are pretty happy with this agreement. So this, sorry?
On your previous slide, if I use the word saw,
Mm-hmm.
can I ask a question that would relate it to the word flying?
So if you ask, when did someone see something, annotators will probably answer flying to Chicago.
Or last month.
Oh, yeah.
And then so flying to Chicago would be a legal answer.
Yes.
What's the agreement on prop bank among expert annotators?
I'm not sure about prop bank, but for Untitled, it's over 90%.
I see. Okay.
Yeah.
What does agreement mean here? Is it F1? Or?
Yeah, so it's F1, but it's a relaxed agreement whenever the answer overlaps with the argument, and we do not consider labels because the space is different. Yeah, thanks. Any other questions?
So you mentioned a manual of 89 pages.
Yeah.
And this seems to be one page. Is
Actually,
there an epiphany, or how did it take so long to come up with a simpler scheme?
so
Data?
it's actually about 5 pages because the questions are templated. So we define a very simple grammar to write the question. So we have to define it a little bit.
But I guess my question is, I think in hindsight, it's 2020, right? It's obvious that this is very simple annotation scheme, and you can get a lot more label data. I was just surprised that it took the community so long to come up with this. That's more like a comment rather than a question.
I see.
Well, here's the question form of the question comment. It seems like usually, right, it's a trade-off, right? When you go from 98 or however many pages to 5 pages, there's some information that presumably the people who are seeing this are not providing. Maybe it's about particular, syntactic fine-grained distinctions. So maybe the question is, what are we losing by going to this simpler scheme?
Yeah, so that's a good question. The information are not very fine-grained. So, for example, the syntactic alternation lies in the actual questions themselves. So if people ask what broke, it's asking about the object, but they ask what broke something, it's asking about subject. So it's a little bit subtle. We're also losing some semantic roles such as discourse, which cannot be asked about, and something like this. Shall we move on? Yeah, so basically, that's what we've done for QA-SRL, which does not require any syntax or frame ontology. In 2016, we had a work that applied this question-answer-based idea to improve a CCG parser. The basic idea is that if the parser is not sure about a particular attachment decision, it can automatically generate multiple choice questions, such as who was flying to Chicago, we or the Grand Canyon. And if the Turker answer we, the parser will know where to attach to. And we observed some modest gain on CCG bank using this crowdsourcing method. And this year, the work led by Julian Michael generalized the idea of QA-SRL to fully crowd-scale and free-form question-answer pairs. And it's no longer restricted to verbal predicates. So for the same sentence, annotators are free to ask what happened when we were flying south of Grand Canyon, and which city were we going to, Chicago. And hopefully this kind of more free-form question-answer pairs can capture higher coverage and richer semantic structure. So
I hope you hear this summer working on that.
Yep. So what I've shown is that we can collect SRL data with crowdsourcing in a cost-efficient way. So the rest of the talk will be focusing on building an accurate SRL model for a prop bank. Traditionally, people solve SRL using pipeline system that involves syntactic parsing. For example, the candidate argument spans are extracted from the syntactic constituency trees, and to assign semantic row labels to the arguments, they build a model that use lexical or syntactic features. And in contrast, the end-to-end SRL system model the problem using as a BIL tagging problem. For example, the work by Zhou and Xu from Baidu Research use deep bidirectional LSTM plus CRF layer, and also use context window features, but not any of the syntactic features that people have used before, and they got state-of-the-art result. But there's some finicky details about the model. As far as I know, several other groups, including me, tried to re-implement the model and failed. And in our work, we further simplified the model by Zhou and Xu by first remove the input context window features and also the CRF layer on top, which also simplified the training process. So I will show you in the next part of the talk how this could work. So if we model SRL as a BIL tagging problem, the input is a sequence of words with the predicate, and the output is a BIL sequence. There's a one-to-one correspondence between the words and the output tag, which kind of simplifies the problem. So BIL means begin inside and outside, which indicates the boundary of the SRL spans. And we can directly read off the final SRL span output deterministically. And this is an overview of our entire model. So there's some implementation details left out, but basically 90% of the information we need to know to re-implement the model is contained in this picture. It's based on a deep bidirectional LSTM tagger. And we added highway connections to make training easier. We also used variational dropout to stop overfitting. And finally, we use Viterbi decoding with hard constraints to enforce the output consistency. So in the next few slides, I'll go through each of the nuggets one by one in detail.
Quick question. So in like your example where there's like two verbs, like you saw the man flying,
Yeah.
how does it work with this model?
So in the prop bank setting, the verbs are provided as input. So two verbs of one sentence correspond to two different training samples. Yeah.
So that's part of the input is the verb.
Yeah.
Are all answers only words? Like we flew over the Grand Canyon.
Mm-hmm.
Where would the Grand Canyon two words fit in this word?
Sorry. So here the,
Okay.
Yeah.
Thanks.
yeah. Cool. Any other questions? So here's the cartoon version of the BiLSTM tagger. The bottom layer is the input, which contains the word sequence and the tag sequence. The tag is a binary tag, which indicates whether the current word is a predicate or not. And they are embedded into 100-dimensional embeddings each and concatenated to feed into a forward LSTM that reads input from left to right and a backward LSTM that reads input from right to left. And the output is projected into a softmax layer. And the final output tag is the one with the highest softmax score. So this is basically how the tagger works. So
What are the tags here? Are they for speech tags or?
the BIL tags for an SRL.
No,
The verb.
No, in the input layer.
Oh,
So you've word and tag embeddings.
yeah, it's a binary tag because
It's just a binary tag for the predicate. Okay.
yes.
Okay. And you still have a 100-dimensional embedding for a binary tag?
Yes, we probably don't need that, but
Okay.
kind of want to keep things symmetric. There's no particular reason for doing that.
I see.
Yeah.
Okay.
So there's a recent trend of using deeper and deeper models for higher accuracy. For example, in grammar as a foreign language, they use 3 layers, and in the work by Zhou and Xu, they use 8 layers by BiLSTM. And also Google's recent neural machine translation model also used 8 BiLSTM layers. And if we go to the land of computer vision, the ResNet has 152 layers. Following the same idea, we stacked multiple bidirectional BiLSTM layers on top. So this greatly increases the expressive power of the model. However, it makes it harder to train because each layer has its nonlinear function, and when we backpropagate, we'll have the vanishing gradient problem.
Is each of those horizontal lines a BiLSTM? Like the way you've drawn this looks a little bit odd. That the forward pass is input to the backward pass?
Exactly.
Is that how you actually implemented it?
Yes.
Oh.
And then it alternates. So forward, backward, forward, backward, forward, backward.
Yes.
I see, okay.
Okay. Did we experiment with the more standard approach?
Yes, so when I was re-implementing the Baidu model, I tried different ways. It didn't seem to make a huge difference, but of course, if we introduce more parameters, that could have an impact on the performance. But we didn't do an apple-to-apple comparison. Yeah.
Does it make decoding harder for training? Like, if you have to alternate forward, backward all the time, does it slow things down or?
I don't think so. If the number of so for Google's neural machine translation model, they use 6 forward and 2 backward, something to exploit parallelism. But for our model, we didn't do that.
Right, and it was like 6 layers, sort of all the forward layers and then all the backward layers, and then they combine them, or?
Yeah, something like that.
I see. Okay.
Theirs is a larger scale thing, so they need
Yeah.
to exploit more parallelism.
Of course.
Maybe if you use the standard BiLSTM, you wouldn't get into vanishing gradient in smaller layers, and you could go
Yeah, so the idea is that if we the number of layers is too many, they'll also always have the problem, I guess.
Right, I mean, that's the matter of too many.
Yeah.
Maybe it's standard, but too many might be weird.
True. Okay. So previous work had tried to cope with this problem with different methods. For example, Zhou and Xu use different learning rates for different layers, like bigger learning rates for bottom layers, something like that. And the other work, including us, used some sort of shortcut connections between layers. They're called the highway or residual connections. So this is how it works. Here's a cartoon version of a BiLSTM block. It reads input xt from the previous layer and ht-1 from the previous time step, and output the ht to the next layer and also the next time step. So the idea of a shortcut connection is to augment the original output ht with the input xt directly. So if we directly add them up, we get a residual net. And if we use a sigmoid gate to trade off how much we want to use the original output and how much we want to use the shortcut output, we get a gated highway network. And this is what we use in our work. Okay, so because the model is very expressive, we need to use dropout to reduce overfitting. And traditionally, dropout masks are only applied to vertical connections in a deep BiLSTM network. So the reason is that if we apply dropout to recurrent connections, and the recurrent connections share the weight matrices across different time steps, if we apply different dropout masks over and over again, there will be too much noise amplification. The information will be lost across time. So there's a nice trick called variational dropout. The idea is very simple. We reuse the same dropout mask for each time step, so that wouldn't cause too much noise amplification. And there's a final caveat left for the decoding part. So if we do greedy decoding for each softmax, and the tagging decision for each word will be independent of each other. And this will result in inconsistent output. For example, an inside of arc0 will be following a beginning of arc1. And we call it a BiL inconsistency, and it kind of hurts performance. So the idea is that we introduce a set of heuristic transition scores where the score for a valid transition is set to 0 and the score for an invalid transition is set to negative infinity. And we run BiL decoding over the softmax scores and the transition scores so we can get a valid sequence with highest score overall. Yes?
So how does this compare to the CRF decoding? Does it work better or worse?
Good question. We did not compare to CRF because in actual implementation, CRF creates a lot of nodes in the computation graph for the forward-backward training time, and it was too slow. And the model already took a week to train, so we didn't try that. Yeah. So here are the other implementation details. We use 8-layer BiLSTM with 3-dimensional hidden layers. For word embedding, we'd use 100-dimensional glove embedding, and they're updated during training. The LCM weight matrices are initialized to normal orthogonal matrices. And for the ensemble result, we use product of experts of 5 models to average the model scores. And the models are trained for 500 epochs, which takes about a week for the PROBANK data set on a single GPU. We report experiment results on 2 data sets. The first one, CoNLL 2005, is the original PROBANK data set. It has the same size as the Pantry Bank, and it only has 1 domain, which is the Newswire Wall Street Journal, and all the predicates are verbs. And the OntoNodes is a bigger data set with 140K sentences. It has more domains, such as telephone conversations, news groups, broadcast news, conversation, weblogs, etc. They also added some nominal predicates for some of the sentences, but not all of them. So basically, it's a larger and noisier data set overall. So here's the results on CoNLL 2005. On the x-axis are all the models, including ours. The model with an asterisk are the ensemble models. Y-axis shows the F1 from 60 to 90. The blue bars are the results on Wall Street Journal, which is the in-domain test set. And the green bars are the out-of-domain test set, which is the brown data set. So we outperformed previous state-of-the-art for both single and ensemble models. And so we can see there's a trend. So there is a great improvement since people have started using bidirectional LCM models. The number on Wall Street Journal test set increased by 2 points when we move from pipeline models to BiLSTM-based models. And for CoNLL 2005, we can see the same trend. For both data sets, our best ensemble models reached 83% F1. So we did some ablation study, first to see the effectiveness of a deeper model. So here the x-axis shows our model with different number of layers from 2 to 8. Y-axis shows the F1 on CoNLL 2005 dataset. So the blue bars are the number with greedy decoding, and the green bars are the result with Viterbi decoding. Overall, the Viterbi decoding has about 1 point improvement over greedy decoding. And the performance increases as the model goes deeper, but the largest jumps come from 2-layer to 4-layer, and after 6 layers, the performance more or less saturates. And also, the 2-layer model benefits a lot more from constraint decoding rather than the deeper models. Yes?
Does the greedy decoding also include the constraints, the hard constraints?
No, it's just greedy for each position. Yeah.
On your previous slide, is it the one after this, sorry. Yeah, and the Zhao model, is it easy to ensemble it and see, like run it with just 5 different random seeds to find the difference?
Yes, it's easy to ensemble, but we don't have the code. Yeah.
That's the result that no one can replicate.
Yes.
Oh, okay.
And Viterbi here, so basically your transition probabilities are just these heuristic scores.
Yes.
That's
But it actually helps a bit, quite a bit, yeah.
yeah, of course.
Okay. So we also want to see how effective each of the deep learning practices are. So here the plot shows the learning curve of different model ablations. X-axis shows the number of epochs from 1 to 500. Y-axis shows the F1 on the depth set. The curve here is the results on the full model, and we are going to ablate each of the practices individually. So if we take away highway connection, the model does worse across the board. And if we take away orthonormal initialization, the model learns very slowly. And actually, in the first 50 epochs, the model's accuracy stays 0%. And it's kind of surprising that an initialization has such a big impact on the model's performance. And if we take away dropout, the model overfits at around 300 epochs. So now we know that the model performs pretty, sorry?
Quick question. Since you are doing ablation studies, have you done an ablation study over how much data you use for training?
No.
How much data do you have to begin with for training?
So that's about 30K sentences. That's about 90K examples. Yeah.
You have to try to put it anyway.
Yeah, that will be interesting, actually. So for the initialization, it doesn't have that much impact on the shallow models, but for the deeper models, it's very crucial. Yeah. Okay, so although we got the safer result, we are not satisfied just presenting the number and call it a day. We want to understand more from the results. So here are the questions we want to ask ourselves. First, what's in the remaining 17%? What's stopping the model from getting, say, 100% accuracy? And when does the model still struggle? And the second question is, we know that the deeper models are effective, but what are they good at really? And the final question is, the BiLSTM-based models are very accurate even without syntax, but can we really conclude that syntax is no longer useful for SRL? So let's start with the first question, when does the model still make mistakes? To analyze this part, we introduce a set of oracle transformations that try to fix different types of errors, starting from the predictions and until the model gets 100% accuracy. So the idea is that we want to tease apart different types of structural errors, such as labeling errors versus boundary errors. And we want to link the different error types to non-linguistic phenomena, such as PP attachment mistakes. So we define a set of oracle transformations. The first one is that when we see a predicted argument has the correct boundary, but the wrong argument label, we fix this label to the gold. And if we see core arguments in the wrong place, we move it to the correct position. And for the next one, we can split a predicted argument into 2 gold arguments if they are consecutive to each other. Or we can combine 2 predicted arguments and merge them into 1 gold argument. And we can fix the span boundary within a certain window and drop a false positive argument or add a false negative argument. Any questions about the transformations? So the plot here shows the improved F1 after each kind of error fixing operation. We compare to the 2 previous models where we can get their predictions, which are by Pradhan and Poynak-Kanak. So we start from the original model prediction, fix the labels, move arguments, merge and split spans, fix boundary, and finally, all the models reach 100% accuracy where all the errors are fixed. So after fixed labels, the error reduction on our model prediction is 29%, which means 29% of the error correspond to labeling errors. And 25% of our model mistakes correspond to the attachment errors. So we'll look at these two kinds of errors in detail. So for labeling errors, we can compute a confusion matrix for the predicted labels and the goal labels. The confusion matrix is normalized by rows. So the matrix shows that arg2 is often confused with certain types of adjuncts, such as direction, location, and manner. And why is this the case? So the answer lies in the prop bank frame files. For example, for the verb move, its argument 2 actually means the goal or the destination. And for the predicate cut, its argument 2 means the direction. And for strike, its argument 2 means the manner or instrument. So basically, they're actually sometimes close to each other in terms of meaning.
You look into how your QA SRL handles these things. Because it seems like this would be exactly the kinds of distinctions that like people wouldn't be able to make, right?
Yeah, that's a good suggestion. So for the CCG parsing work, we actually tried a little bit, trying to design tests to let Turkers to annotate argument adjunct distinction, but completely failed.
Forget it. I mean, Mitch Marcus says that in the Petri bank, so there's this, they meant to remove the CLR tag before they released the Petri bank, but so that's the tag that makes the distinction between arguments and adjuncts for PPs, because annotators couldn't do it.
Yeah.
But they forgot to remove it before they released the tree bank.
Oh, I see.
So, yeah.
Yeah, so basically, this is called argument adjunct distinction, and it's very, very hard even for expert annotators.
So this is why when you were talking about the 80% agreement, that was unlabeled because you didn't know how to turn your QA-SRL reliably into these kinds of labels.
Yeah, that's part of the reason, yeah. So, yeah.
Just a quick question about the previous slide. The different errors are mutually exclusive. I mean, it doesn't matter which.
Yeah, they're not completely mutually exclusive, but we do it sequentially. So
if you would have done it a different order, then maybe it wouldn't be 30%, but 20% because some of the errors you can fix in a different way.
yeah, so we try to start with the more specific error types that we are interested in, and the fixed boundary and the drop and add argument are kind of catch-all things. So yeah, you're right.
Quick question on this slide. So I think you do it in a different way than I would have. It seems like where your model is getting relative to the green and yellow ones is the very last thing, like the drop add arguments.
Yeah.
The rest, everybody's making the same number of errors, especially the yellow and blue ones.
Yeah. Yeah, that's a good observation. Thanks. Yeah, so we have seen examples in the overview, but here's an error that the model has predicted wrong. It says Sumimoto financed the acquisition from Sears, and our model thinks that the financing is from Sears. So it predicts from Sears as the argument 2 of the verb, but actually the acquisition is from Sears, so the entire phrase, the acquisition from Sears, is an argument 1. So this kind of error is captured by the span merge operation in our code transformations. So to quantify this, we look at the 25% of the span merge, span split operations, and to see how many of them involve a prepositional phrase. And it turns out 62 of the span merge or split operations involve a prepositional phrase. And this means that PP attachment actually corresponds to a big source of the error in our model prediction. So here's the takeaway of this part. Traditionally, hard tasks such as argument adjunct distinction and PP attachment decisions are still very challenging for the deep SRL model. So maybe, for example, a good next step would be to use some external information to directly target PP attachment and hopefully improve the model's performance. So here's the second question, what are the deeper models good at? We did two kinds of analysis. The first one is long-range dependencies, where we assess the model's performance on arguments that are far away from the predicate and to see how that change. And the second one is structural consistency, where we see the amount of inconsistent BIO tags in greedy prediction. So for long-range dependencies, we split the arguments into several subsets based on their distance to the predicate by number of words in between. And we evaluate the model's performance on the depth set for each subset of the arguments. So x-axis shows the number of words, y-axis shows the average F1. And we compare between our models with different layers as well as two previous models. So we can see the model's performance deteriorates pretty quickly as the arguments get farther away from the predicate. And from the plot, we can see that the deeper model's performance deteriorates much slower on long-distance predicates. So it's a little bit hard to see all the curves here, but the top three curves correspond to the model with 8, 6, and 4 layers, and the bottom three curves correspond to the model with 2 layers and the 2 previous systems. And the gap between the two groups of curves gets larger and larger for longer distance dependencies. And another thing we're looking at is structural consistency, where we count the amount of inconsistent BIO bigrams and average that by number of tokens. So this tells us how much and how consistent the model's output is. So the 2-layer model makes a fair amount of inconsistent output, where start from 4-layer, the model is pretty on par with each other in terms of consistency. So for a final question, we want to look at, can syntax still help SRL? Remember that prop-bank SRL is annotated on top of pantry bank syntax, and actually more than 98% of the gold SRL spans are syntactic constituents. So in analysis, we want to try that at decoding time, we want to make the predicted argument spans agree more with the gold syntactic structure or a predicted syntactic structure and see if the SRL performance change. And if the performance gets better, we can probably say syntax can still help SRL. So the plot here shows the percentage of predicted arguments that belong into a gold syntax tree versus the actual F1 of the model performance. So we can see that it's interesting that the previous syntax-aware model, although their performance is not that good, but they have higher agreement with syntax compared to our models. So it means that the deeper models is really learning something orthogonal to the syntax, and by adding syntactic information to the SRL models, maybe we can observe some improvement in performance. We do this with...
Sorry, is that something lexical information? How would you characterize that something?
Oh, it's just unlabeled spans. If predict argument span matches unlabeled gold constituent span.
Right, but that's the behavior. Can you characterize this as a very squishy? Well, it's not as good. It's a non-technical question. But what is the model learning?
What is it that the SRL system that's getting that's not syntax? What is it actually getting?
Oh, I see. So it's definitely learning some of the span, lots of the span boundaries, right? It has higher recall than previous systems because it didn't go through the argument pruning stage. So yeah, I guess it's not fair to say it's not learning syntax. It just doesn't have as high agreement as the previous syntax-aware models.
This is all against the gold standard syntax tree.
Yes.
Right. So I guess another question might be how many of the arguments are sort of possible grammatical constituents, right? So is it the case that you get sort of really weird constituent boundaries that could never be part of of a reasonable parse tree for the sentence?
I see.
Right.
Yeah.
It's just not the right analysis for for the meaning of that sentence, but it's still a reasonable syntactic analysis.
Yeah, that makes sense. I haven't looked at it, but like, as far as I've seen the model prediction, I didn't see anything that's really weird.
Right, okay.
Yeah.
So basically that's not an issue, right? So there is sort of probably.
Yeah.
So
I haven't really quantified this, so I can't be sure, yeah. So we use a constraint decoding algorithm. The basic idea is that when we predict a sequence, we penalize the sequence score whenever it predicts a span that doesn't belong to the goal or predicted syntactic tree. So here's the sketch of the equation for the augmented sequence score. It has a penalization term, which is the penalty strength times the number of arguments disagree with the provided syntax. So the constraints are not locally decomposable, so we can use an A-star search to get a sequence with the highest score. I will not go to the details here, though. So here's the result for constraint decoding. We use 3 different sources of syntax, the gold syntax, and the Charniak parser, which published in 2000, and the parser state-of-the-art syntactic parser by D.K. Choi. And if we use gold syntax, we can get a pretty good gain of over 2 points. And if we use the Charniak parser, it actually hurts the model's performance. And if we use the state-of-the-art parser, we can observe a modest gain of about 0.5 when the penalty strength is right. So the x-axis shows different strength of the penalty, and y-axis shows the F1 from 82 to 85. So the takeaway of this part is that we observe modest gain with predicted syntax. So it's although adding syntactic constraints at decoding time is probably the best, not the best way of injecting syntactic information. Maybe in the future we can do some joint training with syntax and semantics and get better improvement. So here's a summarization of this part. In this work, we proposed a new state-of-the-art deep network for end-to-end SRL. We release and code and model. We will release code and model online, and people can play with it. We did in-depth error analysis, indicating where the model worked well and where it still struggled, and linked that to some non-linguistic phenomena. And we also did some syntax-based experiments pointing towards future directions. So now we have moved hopefully a step closer to our dream SRL system. Hopefully in the future we can further explore this direction. For example, we can do some joint training, or we can try semi-supervised learning for domains where there's not much training data. And we can also do multitask learning, combining different sources of SRL supervision, such as PropBank SRL and QA SRL. This concludes my talk. Thank you. I'm happy to answer questions.